Today, we're cracking the code on one of the most famous algorithms in quantum computing, Shor's algorithm. It's a name that gets people really excited, and maybe a little nervous, and we're about to find out exactly why. So let's kick things off with a pretty big question. What if a single algorithm could unravel the very fabric of our digital security? And hey, this isn't some sci-fi plot. This is the real deal, and it's the core reason Shor's algorithm gets so much attention. You know, almost everything we do online, from sending an email to buying something to your online banking, it's all protected by encryption. And that encryption is kind of like a super secure digital lock. It's based on a simple mathematical truth. Multiplying two gigantic prime numbers together is easy for a computer, but trying to go backwards from the result to find those two original primes, whoa, that is brutally difficult for any computer we have today. And this is what we're talking about. This is the unbreakable digital lock, the very foundation of all our online security. So, how would a regular, classical computer try to crack this? Well, it would have to just guess. It would try every single possibility one by one. And for the huge numbers protecting our data, we're talking about a process that could take billions of years. Longer than the age of the universe, actually. That's how secure these locks are. Or, well, how secure we thought they were. And that's where this thing, the quantum key, comes into the picture. See, back in 1994, a mathematician named Shor dreamed up this algorithm, one that could pick this unbreakable lock, and do it incredibly fast. The only catch? You need a whole new kind of computer to actually run it.
Okay, so here's something a lot of people get wrong. You might think Shor's is this purely quantum thing that happens inside some mysterious black box. But nope, it's actually this really brilliant team-up, a partnership between the classical computers we have now and a quantum computer.
This hybrid approach is, well, it's everything. Here's how it works. A classical computer kicks things off and does the final bit of math at the end. But that one impossible part in the middle, that hunt for a hidden secret pattern, it hands that job over to a quantum computer. Once the quantum machine finds that clue, it just passes it back. And boom, the classical computer can solve the whole puzzle, just like that. So, what is this secret pattern that the quantum computer is so good at finding? This, right here, is the magic behind the whole algorithm. It all comes down to something called period finding. Just imagine you've got this super long, messy string of numbers. It looks totally random, right? But what if, buried inside all that chaos, there's a hidden repeating pattern, a rhythm? A normal computer would get totally lost trying to find it. But a quantum computer, it can spot that rhythm almost instantly. That's its superpower. So how does it pull off this magic trick? It's got this amazing quantum toolkit. First, qubits and superposition let the computer look at all the possible patterns at the exact same time. It runs those possibilities through a special math function where the hidden pattern is hiding. And then this incredible tool called the quantum Fourier transform comes in. It's kind of like noise-canceling headphones for math. It filters out all the junk and makes that hidden rhythm, the period, pop out, crystal clear.
Okay, theory is one thing, but let's actually see how this works. We're going to do the classic demo, factoring the number 15. I know, it's a tiny number, but it shows you the mechanics of the algorithm perfectly.
All right, so our mission, find the prime factors of 15. The classical computer gets the ball rolling. It just makes a random guess, a number that isn't a factor. For this example, let's say it picks 7. And now the quantum part begins. So now, using a tool like Qiskit, which is basically a programming language for quantum computers, we build a special quantum circuit. You can think of this circuit as the instruction manual, or maybe the sheet music, for the quantum computer. It has all the steps it needs to find that hidden period, based on our number, 15, and our guess, 7. Okay, so we run the circuit, and what we get back isn't just one clean answer. It's more like a probability map. But just look at these results. You see those peaks? They're perfectly, evenly spaced at 0, 4, 8, and 12. The quantum computer is practically shouting at us. The hidden period, that secret rhythm we were looking for, is 4. That clue, the number 4, goes back to the classical computer. It does a little bit of clever math, and bam, it spits out the factors, 3 and 5. The lock is broken. Now for the number 15, that's, not a big deal. But for a massive 2048-bit number, that is a revolution. All right, so if we have the blueprint, if we know how to do this, why isn't all of our encryption totally broken right now? Well, this is where we need a big dose of reality. The thing is, the gap between the idea of Shor's algorithm and actually doing it in the real world is huge. To break modern encryption, we don't just need a handful of quantum bits or qubits. We'd need thousands, maybe even millions of them. And they have to be almost perfect. The quantum computers we have today are just way too sensitive to what we call noise. Like tiny vibrations or temperature changes can mess up the whole calculation. And the more complex the algorithm is, the more chances there are for an error to ruin everything. Right now, we're living in what scientists call the NISQ era. That stands for Noisy Intermediate Scale Quantum. Basically, it means our machines are amazing, they can already do things classical computers can't, but they're still too small and way too noisy to run Shor's algorithm on any number that actually matters. You know, factoring 15 is a cool party trick. Factoring the key to a bank security system, that's a whole different ballgame.
So you see, Shor's algorithm is the perfect blueprint. It's the master key to our entire digital world. The plan is written, it's right there. The only question left, the one that researchers all over the planet are racing to answer, is when will the hardware finally be powerful enough to build it?